Huh? The capacitance of the capacitor that draws 2 milliamps of current from that one. Okay. Let's take a look at the lab. I have to leave in about 10 minutes, so you're going to need a 1K ohm resistor and 2.1 microfarad capacitor. Summary theory. If a resistor is connected across a sine wave generator, the current is in phase with the applied voltage. If instead of a resistor, we connect a capacitor across the generator, the current is not in phase with the voltage. This is illustrated in figure 19-1. Note that the current and voltage have exactly the same frequency, but the current is leading the voltage by a quarter cycle. Current in the capacitor is directly proportional to the capacitance and the rate of change of voltage. The largest current is when the voltage change is at a maximum. If the capacitance is increased or the frequency is increased, there is more current. This is why a capacitor is sometimes thought of as a high frequency short or shart. Does everybody understand this little drawing here? The current in the circuit is the dotted line. There's the most current in the circuit when the change of voltage is at its maximum. So the rate of change of voltage is going to be the slope of this line. So at this point right here where it's pointing to, the change of voltage is how steep this curve is, right? So at this point, the curve looks like this. Do a little something here. Do a little something. At this point right here, the rate of change or the slope of this is something like that. The rate of change at this point is something like that. So the blue one has a higher rate of change. It's more change of voltage, okay? It's increasing at a rapid rate. Over here at the red point, it's increasing, but at a less rapid rate. Does that make sense? The current is maximum at the bottom peak, so maximum in the opposite direction, where this rate of change is at its maximum decline, right? Does that make sense? Is that funny? Company eBay's just cracking up. All right. If you don't have any questions on that, I'm going to assume you're experts at it, and we'll move on. Okay. Reactance is the opposition to AC current and is measured in ohms. What I'm talking about, like resistance. Capacitive reactance is written with the symbol X sub C and can be defined as this formula, which you guys all love now, and you're just in tune with that formula, where frequency is the generator frequency in hertz, and capacitance is the capacitance in farads. Ohm's law can be generalized to AC circuits. For a capacitor, we can find the voltage across the capacitor using the current and the capacitive reactance. Ohm's law for voltage across capacitor is capacitive voltage equals current times capacitive reactance. Looks like a new formula, but it's not, right? E equals I times R, right? It's just in a capacitive circuit. The resistance is not called resistance, it's called capacitive reactance. Obtain two capacitors with the values shown in 19-1. If you have a capacitance bridge available, measure their capacitance and record in table 19-1. Otherwise, record the listed value of the capacitors. Do you have a capacitive bridge in your tool bag? Is that what that is? Proto board. Yeah. We can take that part and throw it right out the window. We're not measuring the capacitance. We do have meters that will read capacitance, but your meter, your Fluke 117 will read capacitance. If you'd like to, go ahead. If not, just write the listed value. So your measured value right yonder, 0.01 microfarads. Measure the RMS voltage. Oh, shit. Measure and record the value of resistor 1. Okay. I can do that. You all should be able to do this on your own, right? You don't really need me to do this, do you? And if you don't know how to do it, we're not going to shame you, but you know how to read the resistance of your resistor? I've got 0.991 kilo ohms. I'm going to write it on my table as 990.87 ohms. Cool. Set up the circuit shown in figure 19-2. Set the generator for 1 kilohertz sine wave. For the 1 volt RMS output. Whoops. Better way maybe put the glare on the screen. Right now my amplitude is 4 volts peak to peak. I haven't turned the output on yet. I'm just going to set it. Frequency is 1 kilohertz, which is what the lab asked us to do. The amplitude, I'm going to set it for 1. And then, look, you can set it for RMS voltage right here on this third button. 1 volt RMS. You don't have to do any calculations or anything. Isn't that cool? Everybody catch that? Because I just thought, oh, maybe you should have paid attention. Maybe you should have paid attention to the man. The dude abides. The Big Lebowski. Okay. our options on our function generator, you can set the frequency right yonder. I'm already at 1 kilohertz. I'm going to go down to the next button here. This is amplitude. Right now, yours probably says like 1 volt peak to peak.
Yeah.
I'm going to hit the number 1. And then over here on the right, I have options. Volts peak to peak, millivolts peak to peak, volts RMS, millivolts RMS. The lab asks us to do 1 volt RMS, correct? So I'm going to hit 1 and then volts RMS. And look, 1 volt RMS, 1 kilohertz output. That's what the lab asks us to do. Cool? Measure the RMS voltage with your digital multimeter while it's connected to the circuit. You guys should be able to handle that. Check the frequency and the voltage with the oscilloscope. All right, I'm going to set up this circuit on my proto board so you can see how I'm doing it. I don't care how you do it as long as it works. So I got positive on the positive rail. And I got negative on the negative rail. This is where I'm going to put my function generator output. So this is going to give us an alternating current voltage source. This is negative, positive. And then the circuit says we're going to put a one K ohm resistor in series with one of the capacitors. So I'm going to put my capacitor. These things are polarity sensitive, right? And the lab does not tell us if we need to put it any certain way, but it's alternating current, so we shouldn't have to. So I'm just going to connect one to the negative side and one, I'm going to use the resistor to bridge the gap from here to the positive side. Cool, there's my circuit. If I turn that output on, my function generator, check the frequency and voltage with the oscilloscope. I can now measure the output of the function generator, so 1 volts RMS. I can measure right here with my meter. Should read this as 1 volt. And I should be able to check the frequency and the voltage with the oscilloscope. It even gives you 1 volt RMS is 2.8228 volts peak to peak when you're checking that on the scope. The circuit is in a series circuit, so the current in the resistor is the identical current seen by the capacitor. You can find this current easily by applying Ohm's law to the resistor. Measure the voltage across the resistor using the digital multimeter. Record the measured voltage in table 19-2 in the column labeled capacitor C1. Compute the current in the circuit by dividing the measured voltage by the resistance of R1 and enter in the table 19-2. So that's good. We don't even have to measure the current, which I know you guys don't like to do anyway. Why don't we have to measure the current? Right, so this is the last thing I'm going to give you, and then I got to get up on out of here. I will be back, but I don't know that any of you will be here by the time I get back. You guys don't have to stick around. You can stay and work as long as you want. But this is a series circuit, right? You have a resistor in series with a capacitor. So if I were to measure the current here, would it be the same there and there? Current is the same throughout a circuit. So if I check the voltage across the resistor, whatever that voltage value is, I can find the current through that resistor, correct? I is going to be the measured voltage divided by the resistance value, which you had in your table. So mine was like 990 some ohms, right? You want to use your measured value. That's going to give you the most precise value of the current going through that resistor. So is the current in the resistor going to be the same as the current in the capacitor? Yes. If you measure the voltage across the resistor, you can find the current in the resistor. That current is going to be the same as the current going through the capacitor. Okey-doke. Right, I'm going to leave y'all with that, and then I have to shut my stuff down. I will be back later, but I don't know how long it's going to take for them to stab me. So if you need something, shoot me an email, and it should pop up on my phone. Not there, not there, not there. Pick up where we left off on Thursday. I said that. There's a group of high school students coming in to do an FFA competition upstairs. What? What? You're in high school? Yeah. So all those times I talked about your mom, you didn't say anything that was totally kidding. I didn't know you were in high school. That's cool. So you're doing that competition? Yeah. Good, then you can help me run it. Anyway, Thursday will be kind of like here. It'll be open lab. I'm gonna have to run back and forth between the competition and down here. So Thursday is just gonna be lab time. There won't be any lecture. Is there homework due? I think there's homework due. But I'll either post the answers or we'll probably go over it later because other people might not have it done. Anyway. What?
Can you send me an extension? I don't see the extension. You need to use the cable for that, right? To connect this.
What?
To connect the power supply.
Yeah, you don't need these. You can just hook them up there and there.
Okay.
If you want.
Okay. So I see that. You look a little way.
Right. Nope.